energy.
Don't you need activation energy?
So we aren't actually talking about the speed at which the chemical reaction happens. So all chemical reactions will have some kind of activation energy, and that's not actually what we're asking about. Okay, what we're asking about is the difference between our reactants and product energy. Okay, so bringing in the speed as a concept is a neat idea because you're now bringing in unit 1. We're very swiftly now moving out of unit 1, and now we don't care about how fast the reaction happens. We care, does it happen? Okay, what are the things that would control whether it should happen or not? And we'll bring in a term spontaneous eventually. Okay. For me personally, where I like to go with this is actually talk about the inverse. I like to think about it this way. A plus B going to A, B. Okay, and thinking about the heat term within this. Okay. Our heat is ultimately a description of whether we absorbed or released across, so it's the change. Right? Would I expect my products to be lower in energy or higher in energy? So my heat is going to be my products minus reactants. Would I expect the products to be lower in energy or higher in energy? Okay. Where I go with this is physical observations. How many times do I see an element chilling on its own? Yeah, not a lot. Why not? What are the elements doing if they aren't chilling on their own? They react with other elements to make compounds. Why would they react with other elements to make compounds?
To become more stable?
To become more stable, which means my product energy must be lower in energy than my reactant energy. And if I'm going to go through and pick a low number for product, a good low number would be 1. A good high number would be, 100. And I'm going to get a negative 99, right? I'm going to get a negative value. That means heat was released, which means when I go through and run this reaction, I'm going to say heat's released in the formation of that. My products are lower in energy than my elemental reactants. And I'm using the outside world as an example to help me predict this. That's where I go through to think through this overall process. Kind of, sort of? Okay. What we're concerned about ultimately here is how energy is transferred, okay, in the making of breaking of bonds through chemical reactions. Okay. And what we're addressing is what's known as thermodynamics. Okay. It's heat movement. That's thermodynamics, heat movement. So how can we predict and control whether chemical reactions will happen? That's ultimately responsible for our thermodynamics again. It's how those things get quantified and manipulated and arranged to get us those individual systems. Why does it become important? Everything that we work with in the world around us has some transfer of heat. If we understand how that transfer of heat is managed, okay, or controlled, both within just general heat transfer versus chemical bonds making and breaking, we can then start to draw conclusions about what reactions are going to be favorable, what things are we going to have to invest in to provide energy to do certain actions, like cooling down your house. Okay, is that something I need to invest a lot of energy in, okay, to force that to happen? Okay, we can look at it in fuel transportations. Okay, all of those individual systems are now looking at how heat is transferred from one system to another, and how can we understand it and control it. So if we look at a chemical reaction, our atoms far apart start at a high energy state. Okay, so this is what we just walked through. Okay, atoms far apart, and high energy is a little bit kind of a relative term. If we look here, what's high energy? What's our axis say high energy is? 0. Okay, it's a starting point, that's it. Okay, when we bring those atoms near each other, they become more stable. Okay? Because they become more stable, they drop in energy. Why should they become more stable? It's a much harder question. Starting with A plus B, becoming A, B. What's the difference between those? The bond. What's a bond? sharing of electrons. So we could go back to our atoms up here, and let's look at that orange circle. What is that orange circle representing? There's one possible answer that I would argue is not the correct one, but it's clearly written on the screen. What does the orange circle represent? An atom. What part of the atom?
Nucleus?
Okay, cool. Maybe it's representing the nucleus. Okay, well, how big is the nucleus relative to the size of the atom? Not very. In fact, if I put a dot on the screen to represent the nucleus within that, my dot is probably too big. Okay, that's how small our nucleus is. So are we actually looking at the nucleus representing that orange sphere? No, then what's it representing? It's our electron cloud. So when we're going through and looking at those atoms, where can I draw the electron in that orange sphere? Am I allowed to draw it? Come on, pen, work with me. Am I allowed to draw it right there? You see the blue dot? Is that a fair place to draw it? How about here? How about here? Where can I draw it?
Anywhere in there?
Anywhere within the blue sphere. But can I draw it out here?
No.
Okay. We run into a little bit of gray area there. Our representation is typically the 95% probability. So theoretically, we could draw it out there, but for most purposes, it doesn't make sense to draw it outside that circle. Okay, which means our electron is locked into that space. Okay, so now what I want to do is I want to track that one electron through the course of the reaction. So there's my blue dot, that one electron, atoms far apart, and now I bring them to each other, and I now have a bond. Where can I draw my one electron? Okay, in between the two. Is that any different than what I had before? I'd argue no. Remember, I could draw that dot anywhere in that circle, right? Okay. But I would argue where I drew it in the product now, it is in between the two atoms. Where else could I draw it? Could I draw it here? How about here? Here, 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 here. A lot of yeses. How about out here? No, okay. Can I draw it here? Why can I draw it there? There's a chemical bond. The electrons are allowed to be shared in both of those spaces. So when I'm looking at the atoms far apart, my electron can exist only in one orange sphere. What happens when I make a bond? Where can the electron exist? Close. In either of the orange spheres. It can exist in both spaces. Why is it existing in both spaces? Yeah, it's a chemical bond, but how did the chemical bond come about? Why is the electron deciding to share across the other side? What makes it want to go, hey, let's check out the other space? Comes back to your first answer to the question I had a little while ago. Why is the electron jumping atoms? It sees the other nucleus. The other nucleus is positively charged and goes, oh yeah, I can jump over there. And I can hang out with that positive. And so we can get our electrons jumping back and forth. Why is this a lower energy state? Right? Well, let's consider what we do to punish people in the US. What do? We stick them in jail. You mean we put them in a 10 by 10 box and we say you're not allowed to leave. And 10 by 10 is probably being generous. 5 by 5 box and say you're stuck in here. Right? Do better next time. And then next time when you have relieved your duties, served your punishment, whatever that description is. I'm not good with incarceration, apparently. What do we now allow you to do? Be free. Go to other spaces. If an electron can occupy more space, that's freedom. That's lower in energy. We're happy. Despite what you've heard, people in jail, not so happy. Okay? Depends on circumstances. Okay? Our atoms far apart are confined Our electrons are confined. That's a higher energy state. As soon as we go to a bond, now it's a lower energy state. So cool, that makes sense. But now what happens? As we continue to bring the atoms near each other, what happens? It goes up in energy. Well, why does it go up in energy? We now have the nucleuses come back for another showing, and now we're bringing those two positive nuclei near each other. The two positive nuclei want to repel away from each other, and so they're going to spring back and push the atoms apart from each other. So that's why we're seeing effectively a plateau of just its existence to, yay, I've got a bond, now my electrons can jump around, to, oh my God, get away from me. Think about your relationships, right? There's that perfect distance where you're like, oh, this is a good relationship. But then if they get too close, ooh, I didn't like that. Kind of makes sense? Hi? So when we're looking at our chemical reactions, this is another way we consider that, or can consider that energy and those dynamics between them. Of course, since we're now putting in these positives and negatives in the different energy states, all we've looked at is relative energies. But we have defined that they are different. And once we have defined they are different, what could we potentially do with them? Everybody's favorite. Quantify them. And we could now go through and look at the energy of that particular interaction. And as we go through and look at this, just look at the single bonds for the moment. Note the bond energies change. Why would that be true? Are they sharing different electrons? They're sharing more electrons. When I look at a single bond, how many electrons are being shared? 2. How many electrons are being shared? 2. How about that single bond? 2. Do we have different electrons? No. I would argue you're still right. We do have different electrons. What's different about the electrons? Total quantity, sure, but is the total quantity contributing to that bond? At least to a first approximation, no. If we look at hydrogen, hydrogen's electron is a 1s energy level. If I look at chlorine, I'm now jumping up to a 3p energy level. That's changing the energy of the electrons. And if the energy of the electrons is going to change, what's going to happen to the bond? The energy should also change. Not only is the energy of the electron changing, what else is changing? The nucleus. The nucleus is changing in each of those cases, which is now changing the attractive force and pull in each of those systems, which means we're now going to start to evaluate a different energy. Lots of things are changing, which is now going to contribute to a much larger difference in energy distribution for our individual bonds. What happens as we go up to a double or triple bond? What do we note changes? Look at the numbers. 240 goes up to 418, which goes up to 945. As we add more bonds, that energy increases rather drastically. We're talking about more sharing between those systems. Kind of makes sense? Okay? We could then go through and quantify our individual bonds, and we could say a larger bond energy is a stronger bond or a more stable bond, and we could consider the things that could contribute to these. We've already addressed some of those, but we'll come back to that question in a little bit. Okay? If we go through and look at a chemical reaction, we're now transitioning one bond state to another bond state. As we transition those bonds, we're now comparing two different states, a reactant and a product. If our product in energy was lower than our reactants, we've lost energy. Okay? Usually in the form of heat, but it could be light. It could be other ways we could emit that energy. And if we're losing that energy in the course of the reaction, we would call that an exothermic process. And we'd end up with a mathematical symbol of a delta H that was negative. That negative representing the loss of energy through the course of that reaction. If we flipped it and our product energy was higher than our reactants, we'd now be looking at an absorption of energy, and we're looking at endothermic. Mathematically, our delta H comes out to be a positive. Okay? that positive and negative can get very dangerous to talk about. Okay? When I say energy is released, okay, in fact, if I say 500 kilojoules of energy was released, what does that mean? Well, the sign on that number that I just said was positive, right? 500 kilojoules. But because I said released, I'm now looking at it leaving the system. So the English language can interpret a negative sign. And so you have to be careful to understand, is the information you're looking at including embedded language that tells me something about the sign, or am I looking at raw mathematics? The raw mathematics has no language to support it, which is why we need to include the negative and the positive. Kind of, sort of? Okay. Delta H should be review, right? Yeah? It's review because you did that when? Last semester, 151. Okay? So let's go ahead and take a look at this. Based on the bond energies, would you predict this reaction to be endothermic or exothermic? Which is more energetically stable? Okay? Reactants or products. This is something you can work at your tables, discuss through that process, and see what you can come up with. What do you guys think? Okay, exothermic. Okay, if you're saying exothermic, how did you, actually let's not even do that. If you're saying exothermic, what are you saying your delta H is? You don't have to calculate it. Yeah, that's what I wanted.
Oh, yeah.
Okay, if it's exothermic, your value must have been negative. Okay? Because we only have two numbers, how did you run your calculation? Did you do 328 minus 276? Did you do 328 plus 276? How'd you do your calculation?
276 minus.
Okay. Now the question becomes, is that what you should have done? Okay. Is it indeed an exothermic reaction? Okay, because you can say, no, it was endothermic. Well, we'll run into the same question. How are we going to manipulate those numbers? So how do we figure it out? Okay. Products minus your reactants. The 276 corresponded to what? 276 sure looks like it was the products, the reactants. Right? And the other one was our product, wasn't it? But what was the bond energy in reference to? That's how much energy is stored in that bond. So when I go through and look at this chemical reaction, what happens to the carbon-bromine bond? It breaks. What's this energy going to do? Sorry, this one. It's going to be released. So if that energy was released, what should the sign be? $276. Negative. Oh, sorry. Wait. Yes. This is going to come back to our English language with what the bond energy is. 276 was to, where are we stable? With bond or without bond? Which is lower in energy? With bond is lower in energy, which means to break it, what are we doing? We're putting energy in. The language is what bit me on this one. We got to be careful with that. This is the energy that makes us lower. We're breaking that bond, which means I have to add the energy in, which means the sign on that is going to be positive. What happened to the chlorine? It formed that. This is the energy that is a stabilizing factor, okay, which means it had to emit that energy because the bond shifted to a lower energy state, which then means negative. Which means the calculation runs correctly, and what we're confused about is products minus reactants. How do we tie those energy systems in? And this is coming back to the language of those individual systems. Okay? This is one of the reasons why this particular system, I think, is very, very challenging to nuance. Because we would go through and say, well, products minus reactants. And did products minus reactants work? No. Okay? So we have to understand the sign that's being associated with each of these symbols. How is that sign tied back to the information that's being supplied? Kind of, sort of? So we have to hold that information that we started the whole lecture with. Okay? Bond formation versus bond breaking. What does that mean to those individual signs? Kind of make sense? What we could pull out of this is then try and start making formulas and saying, what do we do with all of our bond energies? Okay? Well, if our bond was being broken, bond is being broken, what do we do to the sign? We leave it the same. If the bond is being formed, what do we do to the sign? We invert it. Okay, and we can make it a negative. So we could look at the sum of these energies and then recognize what's happening within that statement of our bond energy. Kind of, sort of? Okay. Actually, there's a different question here. Why is the carbon-chlorine bond stronger than the carbon-bromine bond? Same deal. Etch tables, figure out a vote. Why is carbon-chlorine strong? Some fun questions came out of this. Okay. I'm hearing that the chlorine is smaller, therefore its bond energy should be higher. Well, why is its smaller size matter?
Because it can get closer.
Okay, because it can get closer. What are you talking about getting closer? Is the nucleus what's driving that interaction? It's the electrons. So we don't care necessarily the nucleus is getting smaller. What we're talking about is the energy level for our electrons. It's that outer radius that's dictating the strength of that bond. And the carbon-chlorine bond is going to be a significantly shorter bond because when our orbitals first overlap is with a lower energy level. For the chlorine, it's looking at the 3 energy level. For the bromine, it's looking at the 4. You're looking at a lightly radius. Say again?
It does have to do with like the valence shell.
It has to do with our valence shell. That's going to be our, again, first pass when we go through and look at these. We're looking for that first cut differential between those things. If we wanted to drill deeper, we could in a future chemistry class. At this point, we just want that superficial analysis. Okay? We're looking at the radius being different from chlorine and bromine. How is that going to change the bond strength? Well, for the carbon-chlorine, that's going to bring those two closer to each other. That's going to be harder to break them away. With the carbon-bromine, that bond is now so long, the bromine is effectively not connected anyway. That's why it's a weaker bond, or it manifests as a weaker bond. Kind of make sense? Okay. Back to our energy diagrams. We've got our exothermic, endothermic. One thing that we can look at is if we have stronger bonds in our products, okay, we're looking at an exothermic reaction. Okay. Could we manipulate that on the previous slide? Which bond was stronger, the carbon-bromine or the carbon-chlorine? The carbon-chlorine. Where's the carbon-chlorine bond in our chemical reaction? In our products. If it's stronger in our product side, we got an exothermic reaction. Our products are more energetically stable. In an endothermic system, we're looking at the inverse. The stronger bonds are in the reactants. Okay? So we can use that information to help guide our calculations, as opposed to using a formula to do the calculations for us and then try and interpret it. Does that make sense? That was an awful lot of silence. At least I got a head shake. Okay? You have two different manipulations that you can deal with. Okay? Do you understand the language behind it, or do you understand the raw mathematics? Both of those systems can be useful, and it depends on what you're trying to manipulate. If we're now going to go through and extrapolate this out to bond enthalpy, so now we can just look at the energy for an overall chemical reaction where lots of bonds are being made and broken, we'd want some numerical values that we could bring into it. Okay, the previous example was a little excessively simple, so what we would do is scale up. And in that scale up, somebody has to have determined all of those values. Okay, so what we would end up referencing is tables of data. Okay, but those tables of data are only as useful as the conditions under which they were run. Because if I change the concentration, is that going to change the amount of energy produced? If I change the temperature of the system, is that going to change the energy? Right? So someone went through and said, well, probably because a whole bunch of people presented a whole bunch of data and they had conflicting results. And they had to double back through and say, why were there conflicting results? Oh, well, you ran at a different pressure. You ran at a different temperature. Right? Is that why we're getting different results? We have to control those variables. When we control those variables, our tests can come out and they can produce consistent data. That means when we go through to using the tables, we have to present that we're using that consistent data. Right? And the way we go through and do that is defining what's known as our standard. The standard shows up in a couple different ways. First and foremost, for you, it's that little zero. That little zero in the upper right-hand corner is saying this was run under standard conditions. That becomes important because that now allows me to use all of those tables of data. Okay? Well, what are those standard conditions? Okay, we've heard standard before. You did gas laws, right? We heard STP. What is STP? Standard temperature and pressure. What was standard temperature?
It was like 0 degrees.
Was 0 degrees Celsius. Okay? Which, if you were ever in one of my classes, I then rant about, because what's the point of having a standard at 0 degrees Celsius? Are you ever going to run your experiments at 0 degrees Celsius? That's a nonsense standard to go through and use. Okay? When we talk about thermodynamics, what's our standard state? It's not 0 degrees Celsius. But I thought standard meant we were consistent. It does. It means we're consistent as long as we're talking about one thing. Okay? And if you're like, that's not what standard means, I agree with you. Okay? It's insanely stupid to have a whole bunch of different standards. Pick one and call it standard. And if you don't want to call it standard, or you aren't going to pick one, that's fine too. Just don't call it a standard, because it's not. Okay? In this case, we're calling it a standard. Okay? Again, I would argue incorrectly, but we have to remember the standard state for this. Standard state is 25 degrees Celsius. 1 atmosphere is reasonable, and 1 molar concentration is also reasonable. Okay? Those are pretty easy things to obtain. Okay? And we don't have to go to a freezer to run our experiments. Okay? The next thing we encounter is this big, wicked old calculation. Okay? We'll walk through some of the pieces because some people on Monday seem to struggle with these symbols. What does that E mean? Which, believe it or not, is an E. It's a capital E from the Greek alphabet, and it means sum. It means we're going to add things up. Okay? What's the N mean? The N is the coefficients from the balanced reaction. So whatever you're looking at for your reaction, it's the numbers in front of your coefficient, or in front of your substance. Okay? What's your delta H not F? That whole thing is now a new system, or a new variable, if you will, and technically we would include products as part of it. That is something that we would now go look up. Okay, the delta H naught formation is our standard enthalpy change for the formation of that individual species. Okay? at these standard conditions. So if I want to look at the formation for water, how do I make water? Okay, well, my formation could come from anything. I can make water when hydrogen peroxide decomposes. That produces water. Does that count as a formation? No. Our formation very specifically refers to the elemental states of the elements that made up whatever we're looking at. So if I look at water, water's made up of hydrogen and oxygen. What's the elemental state for hydrogen? Really? Okay, so we go with gas. Yeah, that's a good thing. Okay, and if you're wondering, you could look at the equation. It's a gas. How do I know I'm looking at hydrogen? It says H, right? Elemental state for hydrogen isn't just H gas, it's H2. It's one of those diatomics, so you have to remember that diatomic aspect, okay, for that. Do you know which elements are diatomic? Okay, I just saw a head shake. No, that's okay. You should, in theory, have remembered that from 151. There's a couple different tricks to that, which won't work very well with the lecture recording, and I don't have a pointer. Oh, I do. It's just heavy. We'll point out a couple things that we could go through and do with this. Okay, a lot of people like to go with the 7. So when you take a look at the periodic table, starting at nitrogen, sliding across to fluorine, down to iodine. Looks like a 7, right? Okay. But if you count it out, is that 7 things? No, that was 6 because we forgot one. What was the other one? Hydrogen. Okay. If you like hockey, what does this look like? Nobody likes hockey. That's a hockey stick. Okay? A hockey stick. And to play hockey, I need a hockey stick and a puck. Okay? And then the less, I guess, PC one is have no fear of ice cold beer. And you've got them nailed that way too. Okay? You should know those. You get a cheat sheet. If you don't know them, what should you do right now? Put it on your cheat sheet. Okay? So that way when they show up, you've already got it in front of you and you know what's going on with it. Okay? You may decide it's not worthy to go on your cheat sheet. That's okay. If you still don't have them memorized yet, spend some time, have another sheet of these are the things that I think I need to have memorized. When the next quiz rolls around, you can review that list of things, and if you're like, I've already got those memorized, they don't need to show up on your cheat sheet. If you're like, I didn't memorize that one, put it on your cheat sheet. And you've got ways that you can now develop that cheat sheet before the quiz rolls around. Make sense? Okay. So formation of water, hydrogen and oxygen. What's the elemental state for oxygen? Also a gas. The symbol would be O with the 2 because oxygen is one of those diatomics. Okay? But we encounter an interesting dilemma here. What is that interesting dilemma within this chemical equation? You all did balancing in 151 of chemical equations, right? Is this equation balanced? This is a fun one. We might get people saying yes and no. Okay? The people saying no might be saying no because you can't have fractional atoms in an expression or fractional molecules in an expression. You're not allowed to do that. Welcome to 152. Yes, you can. Okay? We can because of the standard that we've established. When we talk about this, by definition, our formation can only form 1 mole of water. When I look at the formation, the coefficient in front of that product must be the number 1. Everything else is going to get dictated based off of that number being a 1. Okay? Which means you will encounter fractional molecules in a chemical equation. Okay? Why do we do that? We do that because it's the standard for how we manipulate these. If we just balance the equation normally, the numbers that are going to be outputted aren't all going to be the same unit. It's not going to be producing 1 mole of product. It could be 2 or 3 moles, which then means we'd have to factor in another calculation behind that on our numbers. If we just accept as a standard that it must be per 1 mole, it simplifies the data. Okay? So we've got this equation. What we're going to go through and do, if we remember the equation we wanted to use before, it was products minus reactants. And if we've got this memorized, it becomes easy. All we have to go through and do is put it together. So, put it together. So theoretically, when you ran through the calculations, you used the formula, right? Yeah, and you just kind of manipulated it out that way. You'll note I didn't use the formula. Okay? And I also kind of question your 5,000 number, which I don't think I caught on Monday. If that's your number, is this exothermic or endothermic?
It's positive,
It's positive, so it's
so. Endo.
endothermic. Are combustion reactions endothermic? No. The sign becomes really, really important. You should be getting a negative number when you go through and calculating that. Your combustion reaction is exothermic. So we've got to track where that sign comes out. What is all this work that I went through and did? Well, what did I write out for the C4H10? What did I draw up here, that very first line? That is the formation of C4H10 from the individual elements.
Yes.
That's the equation. That's literally what it is. That's what it means when I say formation. Okay? I then wrote down the number. I wrote down the number on the product side. Why did I write down the 1473 on the product side? What does the negative mean? What's the negative mean? Exothermic, which means where's my heat? It's on the product side. I'm using the sign to tell me where to place the heat term. Okay? I then did the formation reactions for all the other ones. So we're getting all of our equations. The 393.5 showing up on the product side again because it's negative. Okay? What's the next thing I went through and did? Okay, we'll see all the way up to C4H10. I put a negative sign there. Why did I put a negative sign there? Is C4H10 a product in my reaction? No, which means I need to flip the equation, which means minus sign. How many times, how many products do I need? C4H10, how many times does it need to show up? 2 times. So what did I do? Multiply by 2. Okay? The next one, our carbon dioxide, 393. It's showing up on the product side. In my equation, where is it showing up? On the product side, so I'm not going to change the sign. How many times does it need to show up? 8 times. That's what shows up in my equation up here. I do the last one. I write that all out. I now have all of these numbers. What can I do with all those numbers and calculations? I can just do all the calculations that run there and I add those all up. This should look kind of familiar. What should this look like? It's named after somebody. I know you're not responsible for names. Hess's law. Remember doing Hess's law calculations in 151? It's Hess's law. It's Hess's law with formation constants. Right? I don't bother to memorize that formula because I never remember, is it products minus reactants or was it reactants minus products or what the hell was it? And I get it confused. So what do? I write out all of the work. This establishes all of the work that I can now navigate the entire system. Okay? In the formula that you guys went through and did, it was what? Products times N. So you took 393 times 8, right? Okay? It was negative, right? So you took negative 393 times 8. You then added negative 241.8 times 10. You then subtracted, there's my minus sign, 147.3 times 2. This is the formula that you're told to memorize or to manipulate. Which system do you find easier to navigate? If you feel it is easier to navigate the equations and interpret that information, you don't have to memorize a formula. But what are you sacrificing? Time. So you've got to decide what is more valuable to you. For me, I decided the time was worth the sacrifice to get it right.
So wouldn't the answer actually be negative 5,860?
800?
5,800, because I did, when you add the
Yeah, can you
2
show
in
the
the
final
product, it's
equation that you put into the calculator?
5,566.
What I would put into the calculator is stepwising all the way through this. Whoops, we got to deal with that. As I would put all of these numbers in, so what is that? About 300?
Yeah,
Negative.
Negative 9.
400 times 8,
Or 200.
2,400? Did I do that right? Ballpark?
Sure.
250 times 10? I should be able to do that one better. I can't in my head.
Those are not.
It should be 3,002.
Yeah, it's 3,148 for the
Yeah.
second one.
4 times 8 is 32,
And then
not
should
24.
be-
And then the
The
next
second
one
one.
is 24. 18.
So what does that come out to be? So I've got a 5, a 600, so 5,300 ballpark, because that one's
Yeah, but
negative.
It's positive.
It's positive. It's positive on which side of the equation?
On the product side.
Product side. And if it's on the product side, that heat was released. That's a negative value.
So
Yeah, that's-
ultimately, the calculation process is correct. You just need to consider the fact that it's releasing heat as it says in the problem, and two.
Both methods are doing the exact same thing. So but you still said 800. I'm getting 3,000, which is the number everybody else is getting.
I don't know that I'm getting wrong.
So this is also one of the reasons why I disliked 151 and 152, because you enter one thing wrong with a minus sign, what happens?
I don't get how you're getting the 53% if we're supposed to combine the two.
Not 2, 3 things.
Well, I'm trying to get the product into a sum of one number.
Yeah.
So that I can.
So
combine.
negative 300 plus 3,200 plus 2,400 gets you what? 5,300. We just ballparked that. That's what it comes out to be. Why should I trust that it's a negative sign? When I did my calculation, where were all those numbers? On the product side. And if it's on the product side, that heat was released. That's got to be a negative value. So how you're getting 58, I don't know, but the numbers there are getting 53. And the numbers in the formula, if you run through the formula, are going to get you that 53 too. So
No,
what we
I
would have to
understand
do
that.
is
I understand.
individually check your calculation all the way through to track it.
I understand how she's getting 5,800 because she's flipping the sign. She's flipping the signs for the products and then getting the sum of that, and then you have products, the sum of the products minus the sum of the reactants. So you have the reactant minus the sum, but she flipped
Yeah.
the signs into.
Yeah, it sounds
Yeah.
to me like what happened is you added the 300, not subtracted the 300. So that's going to be going through and looking very nitpicky at each of your calculation steps along the way. And I can absolutely do that with you to track where that's coming from. Yeah.
So when doing it by the formula,
Yep.
we input the standard enthalpy formation wrong. We don't mess with the Signs.
The whole point of the formula is zero interpretation.
Gotcha,
Yep. Formulas remove all language.
gotcha.
That can be both a good thing and a bad thing. Because what do you end up having to do once you have a number at the end? You usually have to be able to interpret it. If I tell you a negative 5,000, what does that mean? And if you're like, I don't know, that's what the formula told me, that becomes the problem. You have to do a level of interpretation, either at the end of your calculation or at the beginning through the entire process. And you have to decide which method works best for you. How do you know which method works best for you? Try them. Okay? You just saw the time it takes to run through and look at actual individual calculations or individual formulas. Are you willing to invest that time? No? Then you need to run the calculations. Okay? Are you going to get practice with those calculations in this formula? Yeah? Where are you going to get that practice? Say again? Alex, there it is. Your online homework should now expose you to multiple opportunities to go through and run the calculation. Are you getting it correct? Yes? Then there you go. You're doing it right. If you're getting it wrong, then maybe you need to take a step back from the formula and try an alternate method to navigate the system. Does that make sense? So what I'm trying to set you up with is two methodologies to go through and run. Okay? You know else where we can get practice? In class. Do it again. So, if we're going to walk through and do this one, let's get rid of that. We got the trust. Fine. Sum n delta HF products, 0. We're just going to focus on that part for the moment. Okay? So I'm going to start to pull this information out. My calcium oxide and my carbon dioxide are my products. Okay? So I'm going to look for my calcium oxide. Delta H is negative 635.1. We can include the units. Kilojoules per mole times what? I need that N. What's that N? It's the coefficient for that species. So in this case, it's a 1. What are the units on that? Mole. Why are they mole? So your mole units can cancel. The sum is now what we're working on, that E, plus, now I bring in the next term, my carbon dioxide. My carbon dioxide was negative 393.5 kilojoules per mole. What's the coefficient? Still 1 mole. That's the 1. The mole units cancel. That's that first part. That's what that first term means. Everybody okay with that? Here's where everything gets wild. Or actually, not even yet. Note that when we dropped those numbers in, what did we do to the signs? Nothing. We don't change any signs using the mathematical formula. Why? The mathematical formula has already factored all of that information in. It's already part of the system. The only time you manipulate signs is when you're trying to interpret what the mathematical system is saying. Okay? Now here's the dilemma. The next part of our formula is minus and then another sum thing. Right? N delta HF 0 reactants. Okay? What was our reactants? That was our calcium carbonate. So I'm going to write that down. The negative or the delta H was negative 1206.9 What's the N? Whoops, I left off the units. What's the N? Do a little bit better than 1. Yep, someone just corrected it. 1 mole. The mole units cancel. Now I can bust this into the calculator. Okay? For those people that don't trust their calculator skills, I don't trust my calculator skills. I run this as 2 calculations, ultimately 3 calculations. I'm going to run whatever that red number was. Magic number. Negative 630 and 400, about what? Negative 1,000, ballpark-ish. 1,000 kilojoules. Minus, I'm going to do my orange calculation. Ooh, minus a negative. What does that mean? That's now a positive 1206.9 kilojoules. Seeing how the signs cancel? That sign canceling was the bane of my existence. And by was, still is. Okay? Became very hard for me to track and be careful with, so I removed the formula system from it and stuck to the chemical understated. That meant I had to do a whole hell of a lot more work to process it. Okay? Now I can enter it into my calculator, and I'm going to get a value ballpark 206.9 kilojoules. What's the sign on it? Positive. And it wasn't exactly 206 because I did the red calculation to 1,000. What did you guys get for the actual number? Positive, you said 178?
Yeah.
178.3 kilojoules. You track? Which way works consistently for you? Right? That's what you have to stick with. Did we answer the question? What's that? Did we answer the question? No, there was still more to the question. What's the more to the question? There are technically 2 questions. 3 questions. Is it exothermic or endothermic? Endothermic. It's a positive value. Okay, so for me, right away, I would draw a diagram. That's reactants, and I know I'm endothermic going up in energy to the products. Okay, which is energetically more stable? Since I've now drawn my endothermic system, which one is more stable? Which one is lower in energy? The reactants. I have the picture to help me interpret. Because without the picture, I'm looking at a positive number and I don't know what the hell that means. Make sense? The next thing says draw an energy profile diagram. Okay? I didn't understand the mathematics, so I immediately drew a picture. What other information can I add to this energy diagram now? Okay, this becomes fun. Okay, the energy absorbed is right here. There's our delta H. And the difference between those is 178.3 units. What else can I add to my energy diagram? We drew energy diagrams before, right? In fact, if you look at your exam, you should see a whole bunch of energy diagrams, right?
Activation energy?
An activation energy. So is that correct?
Could be. Possible.
Or is it this one? And this becomes a fun question. 2 people immediately responded, okay, to that question. They're possible. I didn't ask if they were possible. I said, which one's correct? And now the appropriate answer is, well, I don't know. I have no context to tell me anything about the transition state and the activation energy. This calculation told me absolutely none of it. The only thing it tells me is that I've got reactants and products. And you brought up a good question too. Oh, it's one step. Is it one step? Does that overall reaction say that this is a mechanistic step? I don't even know if it has 1 hump or 4. Okay? None of that context is visible to me within thermodynamics. I think that's kind of neat. That's why you have to address kinetics and thermodynamics to complete a whole diagram. And if you think back to the kinetic stuff that we went through and did, when you were drawing an energy diagram, there was usually an extra little statement associated with it. It was assume endothermic. Because when we talk about kinetics, it tells us nothing about the energy of the product. So you had to be given just a little bit more information to complete your diagram. Neat. Okay. We'll kind of end it on a semi-cliffhanger. Not really a cliffhanger. We still got 5 minutes. Okay. Does enthalpy tell the whole story? No. Okay. So what this picture is trying to show is that if we just have particles, right? I put solid into a container, it doesn't move around, it just chills there. But as I heat it up, what eventually happens to that solid? It starts to move, and it moves more. Right? Am I breaking any chemical bonds? No, but did I change the energy? Interesting. So a change in energy, I can look at reactant to product, solid to gas, and across that phase change, there's a change in energy, but that change in energy had nothing to do with chemical bonds breaking. And that's a bit of a problem. Because if we're considering thermodynamics and how energy can transfer, and if all we look at is bond energy, there's a whole world of other things out there that don't or can't be explained by that bond energy. So we have to introduce a new term. That new term or new concept is this concept of entropy. Entropy is a bit tricky to deal with. Okay? It's almost always referenced as a measure of disorder. There's a fun little comic here. There's a thing on Instagram. I'm not on Instagram, and apparently you have to be signed into Instagram to make things work. Right? At least it did for me. So if you're interested in taking a look, you can take a look at this. What it's going to talk about is this thing known as microstates. The best definition that has worked for me for entropy is not disorder. It's not microstates. It's possible motion. The more motion I have, or the more possible motion, the more entropy. We can look at a system with 2 halves. This is a low entropy system. That blue ball can occupy either the left half or the right half. This other system now has high entropy. Why? Well, the blue ball could occupy the left half and the right half. The yellow ball could occupy the left half and the right half. So can the pink. And what I have to consider when I look at that system is not each of them individually, but the sum total. One of those possible states is all the colored balls are in the left half. One is they're all in the right half. One is where shown. One is where all the colors are swapped. Those are all different possible states of motion. Since those are different possible states of motion, that's high entropy. Okay? So, entropy of a system increases as the number of ways the matter and energy can be distributed in that system. Those ways are what are referred to as microstates. Okay? So if I get more possible actions for those particles, more motion, that's looking at more entropy. How do we manipulate and use this? This is where we'll cliffhang it. What you should go home and do is determine which of these substances has a greater entropy and explain why. Right? In that go home and explain, this is exactly where we're going to start. You're going to come back and you're going to explain to your table what's going on within that at the very beginning of class. Right? You do have your quizzes back. We're right there at the end, so I'm going to stop the recording.